into the invorticity form. I'm working on the full plane, so the Biot-Savart law for the full plane, you've seen it already several times. Let me just start from my point of departure is Udovich's theorem. So 1963, it's a very nice result that turned 50 last year, just like me, actually. I was born in 63 too. Udovich's theorem is the sort of baseline result, well-positive result for the incompressible 2D Euler equations. And basically it says if you have a vorticity which is bounded and a little bit of decay at infinity, so in this case L1, you have a unique weak solution of the Euler equations. One of the things that you get out of that is if you want to evolve a characteristic function of a set using the Euler equations, you can in a unique manner. And of course, it's not one thing that's not covered by the Udovich's theorem. So there are generalizations, I should say that, to the Udovich's theorem beyond bounded data. But it's really slightly unbounded, logarithmically unbounded data is allowed, but nothing more than that. So the uniqueness for LP vorticities is a classic open problem at this stage for 2D Euler. Okay? Now, so contour dynamics is one example of a kind of evolution that's well defined using Udovich's theorem, and point vortex dynamics is another special case of the Euler equations that you assume that the vorticity is just a finite number of points, and you evolve it using the point vortex system. Again, something you've seen several times on this conference already. And so the issue is how you would like to evolve, or you'd like to describe the evolution of incompressible flow, incompressible 2D flow, with in a situation where the vorticity has some points, very concentrated points, together with a background vorticity which may be smooth, which may be not so smooth, but the point is a superposition of point vortices and a background vorticity field. Okay? And if you want to describe it this way, the natural thing to do from the PD point of view, going back to the equation, is to create some weak form of this equation and just assume this initial vorticity is some kind of measure and work from there. The problem is just assuming the initial vorticity is a general measure and try to solve this equation this way is something that no one ever was able to do it. There's been some attempts to do that, but basically putting Dirac, in this as initial data for this equation and try to make sense of a weak form of the equation with Dirac's initially is way too irregular. Basically, the velocity has a blow-up exactly where the Dirac is concentrated, and it's very hard to make analytical sense of the product U omega. So in 1991, Marchioro and Pulvirenti decided to propose a way of going around this difficulty, and they proposed what I'm calling, or what they called the vortex wave system. And as Eleonora had already described, the vortex wave system is just an evolution equation. It's just a 2D Euler equation, again, in vorticity form, but you separate out the point vortices and evolve them separately using an ODE. So you have, this is the vorticity equation, just evolving the continuous part of the vorticity, the background vorticity, plus of evolution equation for the point vortices itself, for the point vortices. I'm just doing it with a single point vortex because from the point of view of the stock, that there's no cost in doing that. So I'm just assuming for the most part that I'm only talking about the bounded part of vorticity plus one point vortex. And so therefore this would be the sort of classical formulation of the vortex wave system in accordance to Marchioro and Pulvirenti. It's a fair question to ask, where's the wave? Okay? So the point vortex is very clear where it is, but where's the wave? And the vortex is there. I think at this stage, I think that what they were thinking is that the continuous part of the vorticity was the wave in some very, very broad sense of the duality wave, particle wave sort of thinking. I never asked them, so it still remains to. I still want to ask why they call it vortex wave. Every time I give the talk about this, someone complains, "Where's the wave?" So I said, "There's no wave." Okay, but it's not my fault. Marco Puvirenti gave the name. This is just repeating something I just said. The reason why you introduced the system is that you really don't know how to make sense of weak solutions of this problem with measures that include Diracs. It's worth saying that, of course, you have an existence theorem for measures as initial data, but the measures have to be in H-1. And that measures in H-1 implies that the background of the corresponding flow has bounded kinetic energy. And that's exactly the thing that point vortices do not have. So you are able to do positive measures within H-1 due to Delors' theorem, something, again, that was mentioned before. But the Diracs are not in H-1 because the point vortices are not in L2. And this is a difficulty. You cannot make sense of K dot grad delta or K dot grad K, even in weak sense. And that's the difficulty. Now, of course, when you, again, let me go back. What's the issue with this system? And as before, what I'm doing when I say that I evolve the point vortex using the velocity induced by the continuous vortices, is that I'm ignoring the self-induced velocity. And this is an issue that appeared before, I think, in Evelin's talk, for instance. And there is very good justification to say, okay, I ignore the self-induced velocity, and that makes reasonable sense from the point of view of vortex dynamics. But analytically, this is a hard step to take, because if you have to think that this Dirac is really an idealization of a bit of vorticity, and this bit of vorticity may have a very complicated velocity nearby. It doesn't necessarily have, you may say there is some infinities there. In a rough sense, the infinities cancel, but making that precise is something quite hard. And therefore, and if you're doing this in a general sort of, giving a general measure as initial data here and treating this as a PD, this difficulty appears in a very serious manner. So there are treatments. There is a rigorous justification to making the self-induced velocity of a vortex 0. And one example of this justification would be this paper by Marco and Puvirenti, Vortices and Localization on Euler Flows, where they show that if you have very sharply concentrated vorticity, or clumps of very sharply concentrated vorticity, they tend to move around according to the point vortex system, ignoring the self-induced velocity. But this is an asymptotic result that has real serious hypotheses in it. So again, you can do it. There is some justification, but it's not an easy problem by no means, in any way. Okay? And so the point of departure and the Udovich level result for the vortex wave system, the first one was proved by Marco and Puvirenti themselves in '91. They say that if the initial vortices is L-infinity compact support, then there exists a globally defined solution of the vortex wave system. So first existence with the one-point vortex. And if the initial initial place local of the point vortex is not in the support of vortices, then the solution is unique. You can actually reprove the Udovich type uniqueness if you assume the point vortex is outside of the support of vortices. It's a very important issue here. Okay? The essential point, and if you look at the proof of existence and uniqueness, the essential point is exactly to show that the point vortex and the support of vortices stay away from each other. Again, this is not an entirely trivial thing because the velocity near the point vortex wants to be very large, and well, at any rate. So the point is that if the point vortex was inside the support of vorticity, the system becomes dramatically more complicated. Okay? And they themselves made the conjecture that they were somewhat frustrated because they felt that they should have been able to do uniqueness if omega naught was constant near the point P naught, but not necessarily 0. That's still a situation of physical interest. And but this took a while to do. The first result on that direction was due to Starovoitov in '94, and he had to assume the initial vorticity was L-infinity. And going all the way to the sort of the thing that Marco and Puvirenti asked, had to wait for Lacava Mu in 2009. And this is when we sort of started getting interested in the stories when with this paper by Lacave and Mio. Some techniques were developed between in these 15 years that allow you to make this improvement. Okay, so the question itself, the original question, turned out to be quite a bit more subtle than I think Marco and Provirienti expected. So after we got interested in this, and again, this is something Eleonora had already mentioned. Our first result on the story was the existence of a globally defined weak solution with initial vorticity in LP compact supported P greater than 2. And this is something we proved back in 2011. And here we needed to introduce a notion of Eulerian solution. So this is a result of a weak solution, this is a weak Eulerian sense, and whereas everything else sort of Lagrangian sense. I don't think we introduced this. This was already around. And existence for a one-point vortex or for several point vortices with the same sign is global, and up to vortex collision if the point vortices are allowed to change sign. This is the content of this result. So let me just put in the definitions. I think Eleonora never put this definition on the board. So let me put this definition, a definition of Eulerian solution for us to discuss it a bit. Okay. So first, a Lagrangian solution is a solution of the equations which the equations are satisfied in the following sense. You have the existence of a flow map defined outside of the point where the point vortex is into R2 with some regularity, and such that the background vorticity is transported by this flow map. The point vortex is just a solution of its God-given OD in the classical sense. And the flow map is the flow map of the velocity that's induced both by the background vorticity and the point vortex. So this would be a Lagrangian solution. This is, in any reasonable sense, a classical solution to the problem. Okay? And in addition to the existence of this flow map, you assume that it's a volume-preserving homeomorphism from R2 minus the point to itself. Okay? So with all that, this is what a Lagrangian solution means for the vortex wave system. And Eulerian solution, again, this Eleonora had already put out, but an Eulerian solution is just a distributional solution of the vorticity equation together with a mild solution of the ODE. Okay? And there is a fairly substantial difference between this and that if the vorticity is fairly weak. Okay? So now let me say a few words about the proof of Lacave and Mio. Just to why did it take so long to do? Basically because they had to use the Perron-Lyon's theory to do it, even though their flows are fairly smooth. The Diracs in the background actually needed approximations that you needed the stability part of the Perron-Lyon theory to play with. Okay? So the main point of the analysis, of course, is to say that if you initially constant near the point vortex, you stay constant near the point vortex forever. This is the key point in their analysis. But you'll need to use some of the Perron-Lyon's technology to do it, and that wasn't available back in '94. And so, but first they proved that their solution is Eulerian, and then they actually proved the uniqueness and the solution Lagrangian later. Okay. Also, just to say a few words, our proof, and it's again this proof is very close to Eleonora's proof, except that we mollify the contingent part of the velocity. So, in some sense, what we're trying to do is a little less physical than what Eleonora did. So we mollify the continuous part, use the existence part of Marchiori and Provirienti to get an approximate solution sequence with an uniform LP bound. Use elliptic regularity to get the approximate velocity is uniformly continuous. Then use OD Peano's existence argument for ODs to get the vortex trajectory, and finally compactness to get the solution to the weak Eulerian solution to the equation. Okay. Now, this is for P greater than 2, and Eleonora called attention that this P greater than 2 is used to make sense of the nonlinear term in the equations. In fact, if p is less than 2, the velocity is no longer a priori bounded. If p is less than or equal to 2. And the only ODE theory that applies is the Perron-Lyons. And then if you try to use the Perron-Lyons ODE theory to show the existence of the trajectory for the point vortex, you're going to be in trouble because that theory is only almost everywhere, and you're trying to follow the trajectory of a single particle. So you'd be in trouble in many ways if you try to extend this result for p less than or equal to 2. You're sort of in trouble in many different ways. Okay. So again, very briefly, so this is the approximation is done using the approximation here is done using modifying the continuous part of the vorticity. So the approximation, so it's the same result using the approximation by Euler alpha, which we felt was a bit more natural. It gets a slightly more natural result. And that works. This is actually what we were thinking in doing the Euler alpha case. It was a warm-up to doing this with the Navier-Stokes equation. So just regularizing using vanishing viscosity. If you have initial data, which is a smooth distribution of vortices plus point vortices, you have existence and uniqueness of a solution due to a theorem by two of our colleagues here. And Galea and Wayne. So then you take their solution, try to pass to the limit in that. And but it has to be a very hard problem to do, exactly because we have to show that the point vortex, the point vortices don't decohere in the future with a small viscosity, and that. I mean, again, Thierry has already proven this for the point vortex itself, but it's a very hard theorem, and so that remains to be. This would be a step towards to doing the Navier-Stokes case in the future. Okay. So this is the statement of the theorem with Eleonora, but she already went through that. Let me just mention that there is some work, related work, along the same direction by Clayton Bjorn using a different technique, but proving basically the same thing. Okay. So now the next question we looked at is so we ended with the existence of an Eulerian solution to the vortex wave system, and the next thing we asked ourselves is, can we prove that we have some Lagrangian solution at this level of regularity in some way? And let me just say, why would we care about getting a Lagrangian solution, a generalized Lagrangian solution for this problem? The reason is, I think so. The reason is a solution that doesn't transport vortices is not a really very good one. For instance, I don't know that the LP norm is conserved. For the Eulerian solution, the weak Eulerian solutions that I got, I don't know if the LP norms of vorticity or if the vorticity is behaving. How did you say it? It was conserving the. Yeah, well, materially, you use the, well, anyway, so some conservations, some natural conservation laws that apply to that should apply to the vorticity equation, you don't know if you have just an Eulerian solution. But if you are able to produce the transport in appropriate weak sense, then you actually get all these. So the solutions have, the solution, if you get a Lagrangian solution, you have actually a lot more information about what the solution is doing. And but okay, so that's so we would like to look at the problem of producing a Lagrangian solution to this equation. Now, so this is what I'm going to say is joint work with Kripa, Evelyn, and Elena. Okay, so we would like to construct particle trajectories. When you talk about constructing particle trajectories, the velocity field associated to this problem is this: is k convolved with omega. Omega is LPP greater than 2, and therefore this velocity field is W1P for P greater than 2. And this is just a bunch of Diracs. This is just x perp over 2 pi mod x squared centered at P of t. Now, this velocity field is not W1P for any P. In fact, it's not BV. Okay? And it's not BV because, sure, the divergence is 0. The curl is nice omega in LPP greater than 2 plus the Diracs. The curl is a measure, the divergence is 0, but the other first derivatives may not be measures. In fact, they aren't measures in general, they are just distributions. Okay? You can do that calculation explicitly. And for you to be a BV velocity field, you need all the first derivatives to be measured. Okay? So this is not BV, and therefore this velocity field does not fall into the Ambrosio theory. Okay? It's too irregular for that. But it's not a general non-BV vector field. It's a very special one with a W12 velocity plus something which is not BV, but which I understand very well what it is. It's exactly the sum of those point vortices. So the question was, can we extend Ambrosio's theory to cover this game? And the answer is yes. Okay, so so let me first define what it is that we're going to construct. We're going to construct what we call a regular Lagrangian flow associated with this problem. Okay, you take a map. A map is a regular Lagrangian flow if there exists Lebesgue negligible set S, such that for all x in R2 minus S, the map T goes into, this is the velocity field B belongs in L1. This is a Lagrangian map, which is defined except for a negligible set. And well, the push forward measure is controlled. So this is the bounded divergence sort of condition that's applicable here. Okay. So let me just say what the hypotheses are on V to make this kind of the hypothesis. So I'm looking at a velocity field that's V plus H. The hypothesis I'm going to put on V are these three hypotheses are in de Bernard-Lyons and Ambrosio. These are the Ambrosio hypotheses. Control at infinity, L1 into BV log, the divergence is L infinity. These are the Ambrosio conditions. In addition, to be able to add the age of t, I need an extra hypothesis. So the hypothesis is that the V is also L infinity from 0 t into LQ. Just this part has to be LQ for our result to work. Okay. Also, the hypothesis on age, I'm going to take age precisely I mean, of course, I could have done this more general, but why care, right? The age is going to be precisely a sum of vector fields of this form, centered at point z of t, and I'm going to assume the trajectory z of t are Lipschitz. Okay? So the basic velocity field I'm going to work with is V with these hypotheses plus age is a sum of things like x purp over mod x squared centered at point z of t, where z of t is a Lipschitz continuous trajectory. So the theorem is if you let B be such a vector field, satisfying this, with V satisfying this hypothesis, age given as defined, there exists a unique regular Lagrangian flow almost everywhere in R2. And also for almost everywhere in R2, I have that x of the transport of any particle x does not hit z of t. So this is the existence of the Lagrangian map up to here. In fact, and this additional condition tells me one important thing, which was not obvious from the beginning of this story. So let me make a step backwards and say this. Okay. If I'm looking at the vortex wave system, I have a point vortices and a vorticity background, and I look for a solution of this. It is very natural to ask if a mass of vorticity can be exchanged between the point vortex and the background. So it's very natural to ask whether the point vortex, the mass of the point vortex can change, right? And so some of it becomes background, or some of the background goes into the point vortex. Okay? The existence part of our story, the existence theorem that we have, shows that it is of a solution that does not have this, that does not allow that to happen. Okay? But because we are getting particles for which we are getting in the limit particles for which the mass is constant. Okay, but we are not saying with the weak solutions that you couldn't have trajectories, a positive set of trajectories hitting the characteristic, and therefore exchanging mass. So in some very strange manner, keeping the mass of the point constant, but somehow changing the mass of vorticity nearby, changing the amount of vorticity nearby. And with this condition, we're showing that the Lagrangian trajectory does not hit the point for almost all time, you're showing that, okay, that doesn't happen either. So these solutions now, the weak solutions with a Lagrangian flow, really we have existence of a solution that really does not exchange vorticity with the background. Okay? So the proof of this result is an explicit construction. You get approximate Lagrangian trajectories and with an error estimate, and follow ideas that were done both by Lacave and Mion, by Delelis Kripa, you can actually construct this explicitly. I'll say a little bit more about that in a second. But let me point out this: we don't have uniqueness for this problem at this stage. So nothing forbids that there is another solution which does change vorticity between the point vortex and the background. And it's not clear whether this might not be physically desirable. Okay? So this is a question, in some sense, behind the story. If you're looking at a background that's that, yes? Yes. I cannot define what a material domain. Okay, I can define a material domain, but I cannot define a material circle, a material curve, because these Lagrangian maps are only defined up to sets of measure 0. So the answer to your question is I do not know that. Okay, at this level, maybe in some general sense, if I define a circulation as the amount of vorticity in a set of positive measure, but that was the fun of that. Right? So I don't know. So the key idea behind this, the proof, just to extend myself a little bit more, okay, is to show that except for a set of measures. So the key idea really is that, moreover, that I put in the statement of the theorem, to show that particle trajectories do not collide with point vortices. Okay, particle trajectories in fact do not collide with point vortices. If you fix the time, it's easy to see that particle trajectories do not collide with point vortices except for a set of measure 0. What's complicated is if you integrate now on all times, you take a single trajectory and look for all trajectories that hit that trajectory in time backwards, proving that that set has measure 0 is what's complicated here. And there's a very nice estimate that prevents that, which is given in this proposition. So very explicitly, you show that this is the set of all trajectories, defines a set of points x inside a ball, whose trajectories get near to the trajectory z of t any time between 0 and t. So if at any one point in time you get closer than epsilon, you get inside this p epsilon r. And the whole game is to actually do a very explicit, nice calculation that shows that the measure of this set is less than some constant times epsilon to the 1 minus 2 over q. Therefore, it goes to 0 and epsilon goes to 0. Okay, this is the key. I'd say the key point in the proof. Now, so for me to talk about this problem, I should spend a little bit of time talking about the uniqueness issue, because this is really the fun thing that is here, that's left here. Okay. So as I pointed out, so let me just let me go through a couple of pictures just to see what I'm looking at. Okay. These are numerical pictures that I've taken them out of a paper by Schechter and Dubin that came out in 2001 in Physics of Fluids. Okay. And what these are point vortices on a background of vorticity that's varying. You see, there's a gradient of vorticity here that becomes more intense, which is darker, and less intense, negative, more intense negative when it's lighter. So here it's in a disk with a source of circularly symmetric vorticity background initially, a positive and a negative point vortex in it, and here a shear flow again. More intense vorticity in the bottom, positive vorticity in the bottom, more intense negative vorticity on top, and again, a dipole positive and negative point vortices in the background. Now, what I want to call attention is this: if the vorticity was constant near the point vortices, the point vortices themselves, these are blenders. The point vortex is very intense spinning, okay, And if the vorticity is constant near the point vortex, this very intense spinning creates nothing. There is no transport in the background, and therefore it does not create chaos around itself. Okay, so the basic hypothesis of saying the vorticity is constant near the point vortex is saying the point vortices are not generating small scales in the motion. Okay? This is the key issue. Now, the moment that you allow the vorticity to vary in the background, the point vortices create a lot of small scales in the motion instantly, because they mix together the level sets of the background vorticity in a very intense hurricane-like manner. And therefore, as it's pictured in these two examples, the action of the point vortex on the background creates very irregular motions. Now, still, the point vortices are what they are. They just move around with the velocity generated by the background, and the vortice. In both cases, the initial vorticity is smooth. The initial background vorticity is smooth. Of course, as you turn on time, you don't expect this background vorticity to stay smooth, but it should stay. It certainly stays bounded, and it might even stay continuous. Let's not forget about the continuous part, but it should stay bounded. And bounded vorticity is something that you're in the Udovich game, right? So bounded vorticity means the velocity is log Lipschitz, and therefore it should be reasonably nice. The transport outside of the point vortex should be very nice. And therefore, I would say that this should not prevent uniqueness it should not prevent you from proving uniqueness. And it would actually be very nice to go ahead and show you where it does prevent it. I mean, the Udovich argument is a very nice and reasonably subtle one. And once you put in these point vortices, even though you still have the bounded background vorticity a priori, the uniqueness proof breaks down quite dramatically. And this is a very interesting problem. And why is that? The motion of point vortices in a varying vorticity background is a very natural model for very natural rough model for the atmosphere. Okay, the point is rotation of a sphere generates a background vorticity which is naturally generated, has a force in terms of vorticity, a generating term for the vorticity, which is naturally dependent on latitude. So it's naturally something which is not constant on the sphere. And the point vortices are a very natural model for strong spinning in the atmosphere. Therefore, the situation where you have point vortices on a smoothly varying background is a very natural one, very interesting, very natural one. Okay? And therefore, you're only going to be able to say you're happy with this model if you can prove uniqueness for it. And that's exactly so it's an interesting problem, very natural. It's at the edge of being doable, but it's completely far out of what we can do right this minute. Okay. So let me just say this: you should not expect uniqueness so back to what I was saying here. You should not expect uniqueness for the vortex wave system with vorticity in LP for P between 2 and infinity, because at this level you only have velocity, which is C1 alpha, and C1 alpha velocities. ODE theory does not expect a uniqueness for that. Okay, so you don't expect the trajectory of the point vortex to be unique, and therefore there is no reason to expect uniqueness at this level. Okay, you only really should expect uniqueness once you close the vorticity, background vorticity is close to infinity. And this is what I'm saying. So here you don't expect it, but for P equals infinity, it's really very reasonable to expect it, and we would like to be able to prove that. So this is a very nice open problem. So let me just, I guess I'm finishing a little early, but okay. I don't think you guys will mind that. So let me just mention a few open problems in this story. So one thing it would make sense to do, and this is I suspect it's more of an exercise than a real problem, is to redo this the vortex wave theory, everything that's known, the uniqueness, existence and uniqueness with constant vorticity and so on the surface of a rotating sphere, except that in a rotating sphere, you don't expect, even if you start with a constant vorticity, you don't expect to retain it. So that's a complicated story just by itself. But anyways, redoing the existence theory, at least in the rotating sphere, would be nice. The story, there is a story that goes in parallel to this conversation, is what I'm calling here the stuck vortex. And this is a bit of work that this is related to a bit of work we've done with Iftimia and Milton Lopes back in 2003. This is the limiting behavior of a 2D ideal flow index 0 for a small obstacle. If you take a flow index 0 for a small obstacle, you send the obstacle to 0, you very naturally end up with a system that is the 2D order equation with a Dirac vorticity stuck in the point where the obstacle was. Okay? So this is not the vortex wave system, because instead of having the vortex move with the flow, it's just stuck there. But it makes perfectly good sense to ask, well, can we prove things like existence and uniqueness? In fact, existence for this system is part of the work that we've done with Dragos and Elena. But the uniqueness, we actually said it was open. We didn't know how to do it. And one of the things that Lacave and Mio did when their 2009 papers, to say, oh, listen, we answered one of the questions that these three guys had asked, because we had asked if we could prove uniqueness in our case, and well, Lacave, we actually assumed the vorticity was constant near the stuck vortex, so the work by Lacave and Mio in particular also proves uniqueness in our case. Okay, so and so there's this relationship between the problem of the stuck vortex, so therefore the limit of a small obstacle to the other around a small obstacle, and this whole story, the vortex wave system. Okay, one question that I think Evelyn has done some work on this, doing work with looking at the evolution of point vortices with more irregular flows in the background. One thing that you could do, it looks like a horribly complicated thing to do, is to put point vortices, analytic vortex sheets, and prove local existence. You can probably do that, but I wish you luck with that if you want to do it. Probably very complicated, and also treating this in a weak solution sense, you'd need a weaker notional weak solution than what you described here. Maybe that's already there, and also, as I mentioned before, one of the very natural things to look at in this problem is the vanishing viscosity limit. So but that's in the game already, still to be done. Okay. So I guess that's it. Thank you.
Thank you, Milton. Question, remarks?